In this video, we'll be talking about the first derivative test for functions. So let's recall a definition here. It says if a derivative of a function is positive over an interval I, then the function is increasing over that interval. If the derivative of a function is negative over an interval, then the function is decreasing. So I think hopefully this rings a bell, and looking at a graph of this will kind of cement this idea. So looking at this graph, it's broken up into a few different intervals. We have, let me use a different color here. We have this interval to the left of point A. We have the interval between A and B, between B and C, C and D, and then greater than D. So on the graph, or on the function, we see what the derivative is in each of these intervals, and it corresponds to whether the graph is increasing or decreasing. So in the first interval, we have the first derivative is greater than 0, and we can see that the graph is increasing. Between A and B, the derivative is less than 0, the graph is decreasing, and then so on. So whenever the derivative is greater than 0, the graph is increasing, or the value of the function is increasing, we should say. And then when the derivative is less than 0, the value of the function would be decreasing. So a couple things to note. All of the points, so all the points A, B, C, and D on the graph, we call these critical points. Remember, a critical point is whenever the derivative of the function is equal to 0. So at each of these points, the derivative of the function is equal to 0. Another way of saying this is that the slope of the tangent line is horizontal, or the slope of the tangent line is 0, and the tangent line is horizontal here, or the derivative is undefined, which is what we have at point A here. Remember, a sharp turn signifies that the derivative is going to be undefined there. So we have critical points A, B, C, and D, and what we can have at a critical point is there's kind of two situations. We can have the derivative change from positive to negative. I guess three situations. We can have the derivative change from positive to negative. We can have the derivative change from negative to positive at the point. And then the value of the function, or the derivative of the function, can be undefined. So what we see happening at point A here is the derivative goes from positive to negative, and so that point is going to be a local max, right? So when the first derivative changes from positive to negative, we have a local max. The derivative can change from negative to positive, which is what we have here. Okay, so we're going from a derivative of negative to positive, so that's going to be a local min. And then I think I said the third instance is when the derivative is undefined. What I should have said was the third situation is when the derivative doesn't change sign at a critical value, and that's what's happening here at point C. So we're going from a positive derivative, but then we're staying at a positive derivative past that critical point. So this is neither a local max, excuse me, it's neither a local max nor a local min at that point. All right, so three situations the derivative changes signs. That could lead to a local extrema, either a max or a min, or if the sign of the derivative does not change, that really doesn't tell us anything about a local extrema. So what I've just described is a summary of the first derivative test, which says, suppose that f is continuous over some interval I, and it contains the critical point C. If f is differentiable over the interval, except possibly at C, then f of C satisfies one of the following. If f prime is changing from positive to negative at the point C, that's what this is telling us. So less than c, that just means left of the value c on the graph, and then greater than c just means to the right of the value c on the graph, then f prime of c is a local max. Statement B says if f prime is changing from negative to positive as we go left to right, then f of c is a local min. And then if f prime has the same sign as we go from left to right, then it's neither a local max nor a local min. Okay, and that's exactly what that last graph was showing us. It was showing us each of these situations. So once again, let's just highlight where A, B, and C are happening on this graph. So part A is saying if f prime is changing from positive to negative, so that's what's happening right here. So that would be corresponding to part A of the first derivative test. Part B is saying when the derivative is changing from negative to positive, well, that's what's happening here. Left of the critical point B, we're negative, and then to the right, the derivative is positive. And then for part C, this is when we have neither a local max nor a local min, so this point corresponds to part C of the first derivative test. And then what's happening at D, we're going from positive to negative again, so that's like part A of the first derivative test. One last thing I want to highlight here. In the first sentence, or the second sentence, it says, if f is differentiable over the interval, except possibly at the critical point. And so that is what's happening right here. So f prime is undefined. So what this means is, f prime of A is undefined, which just means not differentiable. So that's all that is pointing out, that every critical point is either when the derivative is equal to 0, or the derivative is not defined, or the function is not differentiable at that point. So let's look at a couple examples of where we can apply the first derivative test. The first one says to use the test to find all local extrema for this function, f of x equals 2x cubed plus 3x squared minus 12x minus 3. And recall that local extrema, that just means local max or min. Okay, so in order to do this, we want to find all the places that the first derivative is equal to 0 or where it's undefined. So let's actually find the derivative. So f prime of x, just using the power rule here, we'll have 6x squared plus 6x minus 12. So we want to see where this is equal to 0 and where this is undefined. Well, this is just a regular polynomial function, so polynomial functions are defined over all the real numbers, so this will be defined everywhere. And also polynomials never have sharp corners or sharp turns in them, so this will be defined everywhere, so we don't need to worry about that. We just need to figure out when is this equal to 0. So we need to solve this equation. I'm going to factor out a 6 here. I'm left with x squared plus x minus 2. This is something pretty simple to factor. We're going to have x plus 2, x minus 1. So setting those both equal to 0 and solving, we're going to get x is equal to negative 2, x is equal to positive 1. So what we've done is we found the critical points. These are the critical points for the function. This just means where the function is going to be changing sign from positive to negative, or sorry, I should back up. These are the critical points that tell us where the first derivative is equal to 0. In other words, where is the tangent line horizontal? And so we want to see which of the three situations of the first derivative are going to be happening at each of these critical points. Does the derivative change from negative to positive, positive to negative, or does it keep the same sign when we go from one interval to the next? So how we do this is we can make a number line, and we want to mark down each critical point along the number line, and then we want to test points in each interval to determine the sign of the derivative. In each interval, let's just pick a value and then substitute it into the derivative to see whether we get a positive value or a negative value. I'll test the middle interval first, just because that one's going to be the easiest. And if the value of 0 is in between -2 and 1, so when we put, let me write it like this, when I input 0 into the derivative function, we get 0 plus 0 minus 12, so that's going to be -12. So that is a negative value. So because the value is negative in that interval, that tells us that the function is decreasing between -2 and 1. Now we're going to do something similar for the other intervals. Let's do f prime, how about 2? When we input 2 into the function, I think we end up with 12. Let's try that again. 12, which is a positive value. Really, we don't care whether it's, we don't really care what this number is right here, as long as we know what the sign is. So positive 12, that's going to be an increasing value across that interval. And then let's pick something over here. I'm going to pick a really big negative number, f prime of -100. And the reason to do this is because when we're substituting, sometimes it's easy to just pick really, really big values, because that'll quickly tell us whether we're positive or negative. So I'm not going to actually calculate this out, but when I input a -100 in here, I get a really big positive number for that first term. And then in the second term, I get a negative number. But the first term is going to dominate this function. So when I plug in a -100 in here, the value of the derivative at -100 is going to be a positive here. So that tells us this function is increasing across this interval. Okay, so back to what the original question is asking us. Use the first derivative test to find the local max and local min. So a local max occurs when we go from decreasing to increasing. So what that tells us is we have a local max. Sorry, I said that backwards. We have a local max when we go from increasing to decreasing. So we have a local max at x is equal to -2. And then what I said originally, we have a local min when we go from decreasing to increasing, and that is going to occur when x is equal to 1. And this information is confirmed by the graph that we found. So we found a local max at -2, and then we found a local min at -1, and for the function, and this is confirmed by when we look at the graph. So to the left of -2, so in this interval, the function is decreasing. In this interval, the function is increasing. So I can put a little plus or minus sign here. Then in this interval, sorry, I have this backwards. This interval, we're increasing. Increasing here, decreasing here, and then we're back to increasing. Okay, and then let's look at a second example. Similar idea, find the local extrema for the function f of x is equal to 5x to the 1/3 minus x to the 5/3. So again, to find the local extrema, we need to find the critical points and then test those critical points to see whether the intervals are positive or negative. So to find the critical points, we need to find the derivative of the function. So we're just going to use the power rule again. So we're going to have 5 times 1/3, which is 5/3, x to the 1/3 minus 1. So 1/3 minus 2/3 is going to give us -2/3, minus 5/3 x. 5/3 minus 1, so 5/3 minus 3/3 is going to give us positive 2/3 here. Then I'm just going to simplify this a little bit. So we're going to have 5 over 3x to the 2/3 minus 5 over 3x to the 2/3. And then I want to write this as a single fraction. So to get a common denominator, in each denominator I already have a 3, so I need to multiply the top and bottom by x to the 2/3. So we'll have 5 over 3x to the 2/3 minus 5x. So when we multiply x to the 2/3 times x to the 2/3, we add the exponent, so that's going to be 4/3 divided by 3x to the 2/3. Now we can write this as a single fraction divided by 3x to the 2/3. Then I'm going to do one last thing. I'm going to factor out a 5 in the numerator. So 1 minus x to the 4/3 divided by 3x to the 2/3. Okay, so, we could have stopped up at this point. However, solving that function, or setting that function equal to 0 and solving, could be a little bit messy just with the fractions and the negative exponent. So cleaning things up down like this is going to make the rest of the problem a little bit easier. Okay, so once we have the derivative, we're going to set that derivative equal to 0 and solve. We also need to figure out if this is undefined anywhere. And because we have a rational function, it's going to be undefined at x equals 0. So we're going to keep that point in mind. But first, let's set this equal to 0 and solve. So 1 minus x to the 4/3 divided by 3x to the 2/3 is equal to 0. So a fraction is equal to 0 when the numerator is equal to 0. So we can just set the numerator equal to 0 and solve. So 1 minus x 4/3 is equal to 0. Divide both sides by 5. Okay, so 1 here is going to be equal to x to the 4/3. And then to solve this, well, x is actually going to end up equaling positive or negative 1. So if our x is positive 1 here, we're going to take the third root of positive 1 and raise that to the 4th power. That'll give us a positive 1. If x is negative 1, let's write this out. 1 is equal to negative 1 to the 4/3, which is the same thing as negative 1 third root raised to the 4th power. So the third root of negative 1 is negative 1. Raise that to the 4th power. That's equal to positive 1. And we could do the same thing with positive 1. That will also solve the equation. So we want to use plus or minus 1 here for x. Okay, so those are the critical points. And then we also need to use a 0 because this is when makes the derivative undefined. So these are the 3 values we need to test the intervals for. Or these are the 3 boundary points, I should say, that make up our intervals. Okay? And again, we want to test these values into the derivative function. So in the left interval, I'll test f prime of negative 2. In the second interval, I'll test negative 1/2. In the third interval, I'll test positive 1/2. Oops, I should make this needs to be plus here. So in the third interval, I'll test positive 1/2. And then in the last interval, I guess I'll test positive 2. So finding these values for f prime of negative 2, we get negative 4.02. For f of negative a half, we get about 0.633. For f prime of 1/2, we get positive 0.633. And then for f prime of 2, we're back to negative 4.02. So looking at the values, or the signs, inside these intervals, here we're negative in this interval, we're positive in this interval, positive again, and then negative. So again, deciphering that, we're going to be decreasing in the first interval, increasing here, increasing still, and then decreasing. Okay? And remember, anytime the sign changes, that's when we're going to have a local extrema. So we have two sign changes. We go from decreasing to increasing at negative 1. Then we go from increasing to decreasing at positive 1. So when we go from decreasing to increasing, that's when the function has a local min. And then when we go from increasing to decreasing, that's when we have a local max. All right, so we'll have a local min at x equal negative 1, then we'll have a local max at x equal to positive 1. And this is confirmed by our graph. We have a local min down here, and then we have a local max right here.